All right, so at 10:01, I'm gonna get started and we'll start going through some material in just a moment. But before I do, I want to remind everyone that there are some homeworks due this Friday at 5. So make sure you get those done, particularly the ones here on the algebraic modeling. So the algebraic modeling homeworks due Friday at 5. You can see the homeworks there. But so all of the ones from the algebraic modeling are due Friday at 5. Oh, the remaining ones, I should say. Last Friday, we had homework due too. We had this one. But the 3 types of models, homeworks are due then. All right, so let's go to the last part. Now, this is the bonus part of the algebraic models, okay? But it's a natural thing to do right now because we just got done dealing with rational models. And I said the type of rational models that we are going to be dealing with are the ones that I will give to you, all right? So you're not going to create rational models. And in the same breath, we could say, well, could we have been given any models? Some model that we looked up on Google, as it has been well known and previously known, all right? So maybe somebody already developed a model and it's out for the public, or maybe it's a very famous, physics equation or a famous geometry equation that we typically don't think of. For instance, if you're talking about the area of a rectangle, it's the length times the width of the rectangle, right? When you start out doing math, you're given a lot of these types of equations, right? And they're just given to you. So like I said, physics, this happens, geometry, this happens. And even a lot of the pricing calculations, like the tax models that we were given, the interest models that we were given. Now we kind of justified our interest models, but still a lot of the price calculations we were given. All right. So let's take one from geometry. Let's look at the volume of a pyramid. Well, if you looked up the volume of a pyramid with a square base, the volume of that pyramid would be given to you by the following equation: S squared times H divided by 3. Now, S there stands for side length. H stands for the height of the pyramid. And V obviously stands for volume. So again, this is a pyramid with the square base. So you go look up that formula. You could derive that, but might as well just look it up. Or somebody gives it to you. And once you're given this algebraic formula, it is a model for the value of that pyramid. And therefore, we can ask the same types of questions we did in the previous sections. We can say, for instance, if the base of a pyramid is square with sides of length 30, that's 30 feet, and height of 20 feet. What is the value? Okay. Since I've already been given that model, all I have to do is plug in the right numbers into the right variables. In this case, since we're dealing with side lengths of 30, the 30 goes in for the S. The height of 20. 20 goes in for the H. And then dividing by 3. That's something I can just type into my calculator. So I grab my calculator and I put 30 squared times 20 and then divide by 3. I get 6,000. So the volume of that pyramid is 6,000. Now, I'm not going to ask you to figure out the labels or anything like that, but because we have feet times feet times feet, it turns out a volume is in cubic feet. All right, so the volume is 6,000 cubic feet. You guys know what it means to be a cubic foot? You guys know what that measurement is? It's a, think of it as a box, a block. If I had drawn this better, it would look better. So okay. So it's a block that's a 1 foot by 1 foot by 1 foot block. That's what a cubic foot is. It's a cube that's 1 foot by 1 foot by 1 foot. All dimensions. Cubic. So a cubic foot of anything is things that can fit into a 1 foot by 1 foot by 1 foot block. Right? So it's a cube where all the side, the length, the width, and the height are all 1 foot. That's what it means to be a cubic foot. So it says 6,000 cubic feet. It means 6,000 of those blocks would fit inside the pyramid if you cut them up and reorganize them. Types of things. Doesn't necessarily mean it's a block shape, but if you cut them up and reorganize them, that's what you get. The Great Pyramid of Giza is also a pyramid whose base is a square, or very, very close to a square. Its side lengths are 230.4 meters, and its height is 146.3 meters. I want you to use the formula we just did to calculate the value. of the Great Pyramid of Giza. All right. So let's take a look at this one. Side lengths are 230.4. So I put that in for my S. So put that in, square it, multiply by 146.3 because I put that in for my H, and then divide by 3. Now, when you do that, you end up with 258,8737 point about 54, rounding it to 2 decimal places. So that's a value of over 2.5 million. And since these are in meters, this would be cubic meters. Also, a lot of people will write cubic meters as an M with an exponent of 3. M is the shorthand for meters. 3 is the shorthand for cubic. And the reason that 3 is a shorthand for cubic is because you have 3 dimensions in the cube, right? Length, width, and height. So cubic meters, M cubed, same thing, right? That's the shorthand notation for cubic meters. So if you see that on the labeling, that's what it's standing for. Okay. By the way, that's a gigantic value. That many cubic meters of rock and granite and all that stuff is just mind blowing. It's a lot of stuff. So that's one from geometry. That's an example from geometry. Here's an example from physics. Centripetal force is the force that keeps a body in a curved path. The magnitude of that force is given by M times V squared divided by R. M is the mass of the object that's moving around. V is the velocity of the object. And R is the radius that it's going around, right? So it keeps the body in a curved path. So the mass times the velocity divided by the radius. The mass times velocity squared divided by radius. Does that make sense? We kind of know it. Just draw a very quick picture of the centripetal force. If you have something spinning around in a circle, some object, right? How fast it's spinning, that's your velocity. The mass of the object, your m, and then the radius, the point it's spinning around, is your r. Okay? And so those things combined in that way give you centripetal force. Okay. So you probably guess what we're going to do. We're going to say if the velocity of an object is 40 meters per second, the radius is 10 meters, and the object has a mass of 50 kilograms, what's the centripetal force? Calculate this on your own. All right. So mass was 50 kilograms. Velocity was 40 meters per second. And the radius was 10 meters. So we just typed that in. 50 times 40 squared divided by 10. Doesn't matter. It matters that you are multiplying the 50 times this fraction. But if you want to put it in parentheses or not put it in parentheses, you could put a divide sign without the parentheses. It's not a big deal. And the force comes out to be 8,000. Right? Numerically. By the way, if you ever want to know what the label is on force, they have some specific labels. But if you think of the mass was in kilograms, the velocity is in meters per second, and the radius was in meters, right? So if you square things, you get meters squared over seconds squared divided by meter. One of those meters is going to cancel out with that. So that's meters times kilograms divided by seconds squared. That's kind of a weird label, isn't it? All right. If you take a look, let's go to the internet here real quick. I was trying to do that. Oh, there you go. That's what's known as a Newton. All right. A Newton is a measure of force, and it's 1 kilogram per, excuse me, time meters per second squared. Divided by second squared. Obviously, it's a lot easier to say Newton than it is to say kilograms times meters divided by seconds squared, right? So the measurement of force that we're actually dealing with is newtons. This is not something you're going to be tested on, or not even going to even be in the bonus homework, but I just wanted to point that out, that measures of force are often in newtons. Okay. So this is 8,000 newtons in this example. Newton, obviously named after Isaac Newton. So. Now, lastly, we've seen this formula before, and this one was one that was given to us. Obviously, we kind of looked at how it was derived, how we got to it, but still, it's basically a formula for calculating the amount of annuities and we've used it before. Remember, P stands for payments you're putting in each time, or principals, lots of those. R is your interest rate, M is how many times it's compounded, T is the number of years. M is how many times it's compounded per year, T is the number of years. So we did problems like this earlier. I'll just kind of walk through this. We put in $270 each month. So I know my P is going to be 270, and I also know my M is going to be 12, because we're doing things monthly. We earned an interest rate of 6%, so that means my R is going to be 0.06. How much would we have in the account after 14 years? That means my T is going to be 14. So this was a given model we had dealt with before. And all we have to do is plug in the right numbers into the right spots. Remember, when you're doing this, again, I like to multiply the 12 times 14. That gets 168. So when I type it in, what I do is I type in the whole numerator. So 1 plus 0.06 divided by 12 to the 168th power, and then I minus 1. I like to enter there. And then I divide by this number. Make sure you're dividing this. When you're dividing this, you divide it but you put this thing in parentheses. So divide by, in parentheses, 0.06 divided by 12. And then multiply by 270. And you should get that the amount you have after 14 years is $70,822.29, rounded to 2 decimal places. Is that all right? So again, that's a given model. We were given this. We didn't have to derive it on our own, although we did kind of see where it came from when we got to that point. I'll skip example 4. Example 4 was about half-life of plutonium. Kind of already done one of those with a given model. And so that's the end of chapter 7. Okay. That is the end of chapter 7. So chapter 7 was algebraic models. And we either built them or were given them based on the information in the problem, based on how the situation worked. Okay. Chapter 8 is about regression. And regression is another way to do modeling.